I guess I have like an
Yes, that's right. So welcome everybody to this week's Oxford Discrete Maths and Probability Seminar. It's great to see so many people here. Thank you very much to Shankar Bhamidi for joining us from UNC Chapel Hill. He's going to speak to us about living discretely but thinking continuously. Shankar, over to you.
Okay, thank you. So, I have lots of character flaws, including the inability to spell and also not multitask. So, in case people have questions, please ask at any point. I'm very bad at monitoring chat, etc. So feel free to stop me or whichever way this goes. So, the plan for today is sort of to tell you some new results in dynamic network models and stochastic approximation. And it's not super clear to me, maybe this is like right in your ballpark. I mean, the people in the audience are some of the world's leading experts in, well, discrete math and probability, but I'm not 100% sure, if this is part of your core area or you're interested in this area. So maybe the only goal of this talk from my side is to sort of convey this this is the first time I met my advisor, Aldous. He walked me to the board, and then he basically said, typically in the way that math probability, research in math probability progresses is, there's math probability, and people are sort of pushing out in the frontiers, trying to push out over here, and he finds that sort of hard. So he starts off way far away from the main world of math probability, and then tries to drag the problems back into the main area. And of course, random graphs, random networks is generally a pretty hot area. And so the only sort of goal of this talk from my perspective, towards you is to sort of say that what my general feeling is sort of dynamic networks is like a wide open field for mathematicians. There are tons of problems, many motivated by applications, which I like, and lots of questions where people have no idea, what to do. Okay, so that's it. That's my only goal. So the rest is sort of, I can just relax and talk. So this specific talk, so sort of the main math punchline is the following. So suppose you consider a sequence of growing networks. So vertices keep entering the system and attach in some, according to some mechanism. And suppose this is happening in discrete time. So at each stage, a new vertex comes in, does something. And now suppose you fix your favorite empirical quantity that you maybe care about. So for example, the number of vertices of degree 10 over n. So the proportion of vertices of degree 10. Or maybe something more complicated, the number of vertices whose distance within distance to neighborhood looks like something like this. So the proportion of such vertices. Of course, the natural question over here is, why should you care about this? So we'll get to this at some point. But what the basic punchline of this whole talk is in many network models, which have been proposed in discrete time, continuous time branching processes sort of occur very naturally. So these are continuous time analogs of the discrete time branching processes that show up throughout probabilistic combinatorics. And they sort of describe the limits of such objects. And so I'm going to try to give you, probably in the time that I have, two main areas. So the first one is sort of attributed network models. What are the fundamental questions in this area? What's the use that you can use? And sort of maybe not proof ideas, but generally how, owing to some sort of propagation of chaos type results, you're led to continuous time branching process approximations, which then lead to sort of math understanding. So that's the first area I'll sort of try to tell you about. And then the second area is change point detection, where something happens that shocks the system abruptly. And so the mechanism of evolution changes. So mathematically, what kinds of surprises do you get? And if I have time, I'll try to also say a little bit about seed detection in dynamic networks, but probably won't get time. Okay, so what's the sort of summary finding? So these dynamic network models, they're quite complicated. Even simple rules give rise to complex phenomena. And these are actually hard to predict even from simulation. So this is, again, for me also in this age of AI, it's always surprising that even simulations and reasonable size systems doesn't quite give you the truth until you dig through the math. And so as I mentioned, so either explicitly, like you can take your discrete time model and embed them directly into a continuous time framework. so that stopping this process at appropriate times gives you your discrete time model. So either explicitly or implicitly, because of some sort of approximation that happens when the network becomes large, these dynamics are often driven towards continuous time branching processes. And the basic punchline is, so continuous time branching processes have a very long history, going back all the way to Euler. And in particular, these great Swedish mathematicians, Jagers and Nerman, in the 1970s and 80s, sort of did extensive work on them. And one of the punchlines is many of these continuous time branching processes grow exponentially according to some rate, lambda, often called the Malthusian rate of growth. And whereas functionals that you might care about in a specific model, like degree distribution or page rank scores, they grow according to a different rate. And sort of, let's call this alpha functional. And the interplay between these two rates basically gives you asymptotics. So these are the sort of three summary findings that seem to pop up. Okay, so let's get into sort of the first area, sort of attributed network models. So this is sort of motivated by social networks. So most social networks, they consist of attributes, vertices with different attributes. All of us humans, hopefully we think we're infinite dimensionally complex, but for the context of this talk, I'm just going to think about each individual having a finite a finite set of attributes. And so, for example, if there are just two attributes, one or two, I will sometimes refer to this as minority and majority. But the evolution, so these networks are typically dynamic, and the connections that are formed as the process evolves, there's sort of heterogeneity of connection. So depending upon the types of individuals in social networks, there's one kind of phenomena is homophily, where individuals of the same type have higher propensity of connection. Heterophily is where individuals of different types have higher propensity of connection. So the types sort of influence how connections are formed. But these are also time and path dependent. So people who become maybe popular, start accumulating influence or friends, they tend to have higher propensity of aggregating more connections. We see this when we sort of do Google Scholar and cite references in our papers as well. And but in the context of social networks, once these networks are formed, they play sort of a major role in how information sort of diffuses, how we get information. It plays a major role in how companies sort of judge individuals and decide to monetize, like give money to them to sort of propagate a specific product, for example. And in the area of social networks, there's sort of a number of folk theorems. So for example, one prevalent folk theorem, so folk theorem, namely accepted wisdom, is most centrality scores, like the way that you measure how popular individuals are, whether you measure them by the number of friends they have, or more complicated functionals like their page rank scores, which I'll tell you in a bit, they sort of have the same sort of behavior. So this is sort of some of these accepted wisdoms. And sort of related, maybe at first sight, okay, so an important question is the following. So many cases you cannot actually observe the network, but maybe you're really interested. So a specific setting for this talk is maybe there's a rare minority in the network. So an example of this is, I heard a talk over here. So UNC and Duke have these huge Duke, which is the university next door to us. They have these huge population centers, which are very famous, do lots of surveys, etc. And at the start of the COVID pandemic in the early 2020s, they were interested. The Research Triangle is the area that I'm in, the three big universities, Duke, NC State, UNC. Chapel Hill, and in the middle is where there are lots of tech, etc. And within this population, there's an Asian immigrant population, which is small, has its own mechanism of how it sort of forms social connections. So it's a rare minority, and they were interested in sort of understanding the impact of COVID. So the goal was, how do you sample from this population and then understand their sort of feelings, mental health, and so on. So so this sampling question plays a big role, and within these attributed networks. And so because of all of these reasons, this has motivated like a huge development of network models, like understanding how these maybe social networks evolve over time, what kinds of interventions can you do, sort of making up, this text over here conveys much better what I'm trying to say, but basically trying to get synthetic frameworks where you can play around and understand various things that you might be interested in. Okay, so what's the main model in town? And so I should mention this model, has been around for a while. In fact, in your neck of the woods, sort of, I guess this is Zoom talk, but I'm thinking about this as Christina's and Alex's seminars. Apologies. So in your neck of the woods, Jonathan Jordan, who I guess is currently at University of Sheffield, all the way in 2013 did sort of fundamental work on this. But then there was kind of tapered off, not much interest. And then in the early sort of 2018s, when again these attributed network models or attributed networks became of interest, this same model again sort of took off. So what's the main model in town? So again, we have this latent collection of types, I'm sorry. So we're going to fix two specific things. We're going to fix a probability measure on this types, so the proportion of different vertices of different types. And we're going to fix a potentially asymmetric kernel or function from this type space across type space to R plus. And so what this measures is the propensity of pairs of different types of vertices to connect. And so ignore this, gamma is going to just be equal to 1 in this entire talk. And so what's the basic model? I'm going to call this model script P. So you start with some base model at time 1. And at each stage, a new vertex enters the system. The type of the vertex is sampled according to distribution pi. So independent of what the current state of the network is. And so for vertices in the network, I'm going to call degree of vertex V, dig Vn. This is the degree of V at time n. So this new vertex, so I've sampled this new vertex vertices type. And so conditional on its type and the present configuration of the graph, the probability that this new vertex connects to a present vertex in the graph is proportional to sort of the propensity, this kernel of the present vertex of the graph, its attribute, the attribute of the new vertex that's entering the system, times the degree of this present vertex in the graph, this already existing vertex in the graph. Okay, so sort of lots of words here, but what's the bottom line? So two things play a role. The type of individuals in the graph, the new vertex coming in, and the individual that's already there in the graph, and the current degree, how popular the vertex that's already in the graph, how popular it is. These two things influence how this network evolves over time. Now, the version that I'm telling you here is you mainly get trees because at each stage you only form one connection. This is just to sort of make the talk more slightly accessible, not put too much sort of notation. Extensions of this where individuals come in with more than one edge which they want to connect to the existing graph, or the number of vertices, number of edges that they come in with depends on the type of the individual. All of these extensions one can do. But I'm just trying to tell you the base version where you're going to just end up getting a sequence of growing trees. Okay, so this is the basic model. So before I move on, any questions? Okay, so sort of this interpretation of the kernel. So I sort of have a very hard time dealing with matrices. So the second coordinate over here, this is sort of the new individual that's entering the system, its type. And the first coordinate sort of is the present vertex that's already in the system. And so what this is saying is this number, this measures the propensity of this new vertex, namely type Corgi, to connect to an existing vertex, in this case, type Shibu. Okay, and so what do people care about? So there are various functionals that one cares about. Maybe they're interested in the degree distribution of the graph. So number of vertices which have degree k, and the proportion of these. More importantly, they're interested in joint distribution across attributes and types. So number of joint distribution. Sort of page rank scores of individuals in the graph. So in words, forgetting about all these formulas, it's basically so I'm going to be thinking about our graphs as being directed. So every time a new vertex, I guess I don't quite mention this here, but every time a new vertex enters the system, when it connects to a pre-existing vertex, I think about this as an edge starting from this new vertex and pointed towards the vertex that it connects to. So I'm thinking about these as directed graphs. And so PageRank scores, again, probably clear for all of you in this audience here, but it's the stationary. So I need a parameter C, the so-called damping factor. And so what this PageRank score is just a stationary distribution of the random walk, where at each stage with probability C, I do the usual random walk transition using the edges in the graph. Whereas with probability 1 minus C, I sort of teleport to a randomly selected vertex in the entire graph. And the stationary distribution of this specific dynamics, that's called the PageRank score of individuals in the graph. And it's one way of measuring how important individuals are in the graph. So what people care about is, so for example, what's the distribution of these PageRank scores? And how do these centrality scores, so how do these PageRank scores depend on the attribute type? Okay, so these are the sorts of questions that people care about. So, this model sort of goes back to 2013 and probably even before 2013, the probability community, where Jordan did fundamental work in analyzing rigorously not just in the model that I told you, but in actually an infinite dimensional context, the degree distribution of the graph. So, and then subsequently, there's been a lot of work on functionals, basically like the degree distribution of the graph. But beyond this, it's kind of been hard to analyze this model. So I'm going to call this model script P. Please analyze this model. And now what I'm going to do is I'm going to analyze, I'm going to tell you a related model, which I'm going to call script U. And maybe the way to think about this is useful, maybe, because I've not yet told you why this new model is useful in any way. So what is this new model? So remember, so the original model had this kernel, kappa, and a parameter pi, the distribution of vertices of different types. This new model will take as its input this kernel kappa and a new, I'm just going to call this a weight measure because I don't usually need to normalize this to form a probability measure, nu. And what this model, this is again a sequence of growing trees. And the way that this model evolves is the following. So conditional on the system up to time n, the probability that the new vertex's type is of type A star and it connects to this existing vertex V is given by this kappa AV A star times nu A star times the degree of the vertex at time n, degree of the vertex V at time n. So definitely looks related to the previous model. But the slight issue over here is the types of individuals that are being born into the system and the connections that they form, they're all sort of tightly coupled. Okay, so in particular, the proportion of vertices of different types, this is a random distribution that changes over time. So as a starting point, this seems like, what's the point of introducing this new model? And the reason we introduced this was because of a math error, because I thought that this model is equivalent to the previous model. So I was like happily going off claiming lots of things while I was writing down on my notebook, and then I was about to send it to my co-authors, and then I realized, bad math fact to be now recorded forever on YouTube. Okay, but let's continue with this sort of mistake. So we've introduced this new model script U. Now, the one reason why this model U is easier than the previous model is it can be simulated really easily. In particular, it can be simulated as a multi-type branching process. Okay, so suppose you wanted to simulate this model class script U, then basically what you do is every vertex V that enters the system, it starts giving birth. So you start with an individual of type A, let's say, at time 0. Now, every individual that enters the system, it doesn't care about the rest of the population. The way that it behaves is it gives birth to other individuals in continuous time. So it gives birth to new individuals of different types. And the rate at which it gives birth to new individuals of different types is at any given time, if the number of children that this individual already has is some d, then the rate at which it gives birth to a new individual of type A prime is at rate, this new A times kappa A comma A prime is the new individual it's trying to give birth to, times the present degree of this vertex. Okay, so bottom line, every individual keeps giving birth to new individuals of different types according to specified rates. And so this is a continuous time branching process, a multi-type continuous time branching process. And what you can check is if you stop this branching process when it's of size n, so let the stopping time Tn be the time where this branching process grows to be of size n, then the sequence of graphs that you end up getting exactly has this model class script view. Okay, so this is sort of very easy to check. So bottom line, this second model class script view is much easier to check. Is much easier to simulate. So now, we started this by making a mistake, which is thinking that the model class script view was script P. But now let's continue this sort of this analogy, and let's do this sort of math curiosity question. Suppose there's a way to choose this weight measure nu, so that asymptotically, as you evolve this branching process, you keep running this branching process, the proportion of different types is a random measure, but maybe it stabilizes. And in particular, it stabilizes to this proportion pi that you want in your original model class script pi, the script p. Suppose you're able to choose this nu so that this happens, the proportion of different types stabilizes. Then can you say that in some way these two models are similar at least asymptotically in some manner? Okay, so that's the basic math curiosity question. So this is the basic punchline of this part of the talk. And so the answer is yes. So in fact, there is a way to carry out this entire program. So this model class, other than the degree distribution, has been hard to understand. We want to understand asymptotics for complicated functionals, but it's been hard. But suppose someone comes to my office, they give me, the model that they're interested in, the proportion of different types, and the kernel. In the next few slides, I'm going to give you formulas for how to use these things to get this weight measure nu. From this weight measure nu, I'm going to simulate this branching process, script u. And this is easy to analyze. And properties about this give basically all again, very sort of, okay, most of the asymptotics that you might care about for this script p, you're able to get using sort of this mechanism. So this is the basic conceptual point of this first part of this talk. Okay, so more details about how one walks this path. So again, what's the goal? We are interested in the model class script P, and the inputs, someone comes to my office, gives me these proportions pi of different attribute types, and this kernel kappa, which indicates how individuals of different types sort of have propensities to connect. Then what I'm going to do, and so this functional was formed by Jordan in 2013 when he was analyzing the degree distribution. So this functional, so I'm going to look at the space of probability measures on this attribute space. And on this space, I'm going to form this functional. Okay, so the inputs are this proportion, this pi, and these kernels. Okay, so it's some sort of functional. It turns out that it's convex. It has very nice properties. And in particular, there's a unique minimizer on this space. There's a unique minimizer of this function on this space. So let me call that minimizer eta. So once I have this eta, what I'm going to do is I'm going to feed it into this formula. So I have the eta over here, I have the kernel that they gave me, and I have this proportion pi. Ignore these quantities. These show up in the statement of the results. But this is my weight measure nu. And so what's the punchline over here? So consider this model class script u, where I use the kernel that they gave me and this new weight measure nu. And one can actually check that this weight measure nu in many cases is very different from this distribution of different types, that namely this pi. It's actually very different. So okay, But so right now, the only redeeming feature of this model class script2 is it's easy to simulate as a branching process, at least in continuous time, because individuals behave independently. And so now the question is, so does this give us anything else? And so this is sort of joint work with Nelson, who's at University of Porto, Sayan Banerjee, and Vladis Pipires, both of them a faculty here at UNC Chapel Hill. So what this first thing says is, again, just paraphrased, is sort of asymptotics of all local functionals of this model class script that you care about can be obtained from this model class script. Okay, so to give one specific example, so pick a vertex at random in this model that you care about, and suppose you're interested in local neighborhoods, or in particular asymptotics of local neighborhoods around this randomly selected vertex. And maybe what you're interested in, just to make things even simpler, is you're interested in, when I say local neighborhoods, you're interested in, you pick this vertex at random, you're interested in the individuals that come after this vertex who connect to this particular vertex by time n. So, namely the descendant subtree of that vertex. So as n goes to infinity, as the network becomes large in this model that you care about, the distribution has the following description. So pick a type A according to distribution pi. Starting from this type, run a branching process. So you're simulating this model class script2, namely a branching process, started with a vertex of type A, and run this branching process only for a finite amount of time. But how long should you run this branching process? Run it for an exponential a random variable, which has an exponential distribution, again, independent of this branching process. An exponential random variable with rate equals 2. Okay, so run this, you're going to end up getting a random finite tree, and in general, a distribution on the space of finite trees. This distribution gives you the asymptotics of the sort of local neighborhood for this model class script P. Okay, and okay, so any questions over here? Okay, so so underneath this hood is sort of this branching process script2 with all these design choices. It grows at rate. So the Malthusian rate of growth of this branching process is equal to 2. So one way of thinking about this is, if I just ran this branching process in my computer and I wanted to wait until this system became of size n, I would have to wait around time half log n before this branching process reaches size n. So why is this sort of useful? So this approximating branching process, script2, grows like e to the 2t. So it turns out, if you look at a vertex of type A in this branching process, the number of children that it has, also grows exponentially according to a different rate. It grows like e to the phi at, where phi a is this formula, which again, is over here, not too important. The main point being, these are all formulas that one obtains after going through the sequence of steps, and these formulas give us sort of initially information about this model class script2. So, but the interplay between this 2 over here and this constant phi a over here, what this gives rise to is the following. So for this model class script P, if you're interested in the degree distribution of vertices of type A, then this converges as n goes to infinity to a limit probability mass function, where the limit probability mass function has this form. This was already derived by Jordan, sort of using stochastic approximation techniques in 2013. And the key point here is the exponent of the degree distribution of vertices of type A. They do depend on the type of the individual. Okay, so the sort of news you can use is degree distribution tails. They do depend on the attribute type. So measuring individuals according to the degree distribution, like how many friends they have, namely degree centrality, that does depend on the type of the individual. So these centrality scores depend in a non-trivial manner on the type of the vertex. 9:30. Okay, so I'll try to speed up a little bit. So But now suppose you look at the PageRank scores of individuals. So PageRank scores, at least for trees, have this sort of nice explicit formula. So if you have a tree, then the PageRank score, so forget about randomness for the time being, I give you a directed tree, you look at a vertex V, and you're interested in a parameter C, the damping factor, you're interested in the PageRank score of this individual. Then on a tree, this is nothing other than the following, so ignore this for the time being, just a constant. It's a weight of 1 for yourself, plus C times the number of descendants that you have, so the number of individuals who point towards you. So in our dynamic network process, these are individuals who came after you, who decided to connect to you, plus C squared times the number of individuals who came after that, who connected to your descendants, namely vertices at distance 2 from you, or descendants up to distance 2 from you, and then C cubed times the number of descendants at distance 3 from you, etc. Okay, so for us in probability, so this is of course well known, but for us in our world of probability, this immediately suggests that this is sort of like percolation on some sort of tree, because you're retaining individuals at distance 1 with probability C, individuals at distance 2 with probability C squared, etc. So you're retaining each edge. If you do percolation on a tree, where you retain each edge with probability C, this is basically the expected number of the expected component size that's connected to you. Okay, and so once we understand this conceptual insight, then we can sort of hit the ground running. So we have our model class script P, and we're interested in PageRank scores. So because of this factor n, I'm going to look at the normalized PageRank scores. I'm just going to multiply each of these PageRank scores by n, and I'm interested in the distribution of this object. In particular, I'm interested in this empirical distribution, and I'm interested in understanding, does this somehow depend on the attribute type? Is there a relationship between this distribution? So if I look at this, but only restricted to individuals of attribute A or attribute B, etc., what does that look like? So what's the basic algorithm? I'm interested in my model class script P. What the folk wisdom is once again, these PageRank score distributions should depend, at least in large system sizes, on the attribute type. So minority vertices, for example, should have a different PageRank distribution, at least in terms of their exponents, tail exponents, as majority vertices in two-type attribute settings. So let me try to understand if this is actually true mathematically. So I go back to my model class script U. I consider percolation on this model class script U because of this conceptual insight. Now, if you have a branching process, and for a branching process, you retain each edge with probability C and delete it with probability 1 minus C, once again, you get another branching process. So these percolation branching processes are very easy to analyze. And so I can understand percolation on this model class script U. And it turns out all the asymptotics I might care about for model class script P, I get from this model class script U. Okay, so maybe I'm going to ignore some of these. So there'll be lots of formulas here. Let me just try to explain these in words. So when trying to understand percolation on this model class script U, I end up getting various matrices. So I should say we end up getting various matrices. And so there's some specific matrix that one ends up getting, and let lambda C be the Perron-Frobenius eigenvalue of this complicated matrix. So the interpretation of this lambda C is, it's nothing other than the rate of growth of this percolated branching process. So I look at the original branching process script U, I look at the percolated version of it. It's again a branching process, and this lambda C basically controls how quickly this percolated branching process grows. Now, why is this useful? So for my model class script P, the basic punchline is the following. We can derive joint distribution asymptotics of the attribute types and the corresponding PageRank scores. You end up getting some sort of limit, which the limit object comes from this model class script U. But the basic punchline is, irrespective of the attribute type, if you look at extremal behavior of this PageRank scores. So the extremal behavior, so these tend to have heavy tails. But the extremal behavior, the tail exponent doesn't depend on the attribute type. It's whether, irrespective of what attribute you choose, the tail exponent is the same. It's given by 2 over this lambda c. Once again, 2 is because of the rate of the growth of the underlying branching process, script u. Lambda c is because of the underlying rate of growth of, the rate of growth of the percolated branching process. And the interplay between each of these gives rise to the tail exponents of the PageRank distribution. But the punchline is news you can use, sort of these PageRank score distributions, at least in terms of extremal behavior, they do not depend on the attribute type as compared to sort of the degree distribution. So this sort of negates some of the standard assumptions, or at least wisdom, accepted wisdom for in social networks, at least for this these network models. How applicable this is in real world settings, this is sort of less known. Okay, so these results also give insight into these network sampling questions that I sort of mentioned, but I'm going to skip over all of this and in maybe just 10 minutes sort of tell you one related problem and then stop. So what is the insight that we glean from this above analysis? So in the natural, when I say natural, I mean if you are able to find some sort of approximating branching process, then various things grow exponentially. So when things grow exponentially, again, this is in quotes, what this should imply is the signature of what happens way back in time should like somehow stay there. So an example of this is sort of the Polya-Ern scheme, where what happens way back in time in the evolution of the Polya-Ern scheme, it sort of has a big impact in the evolution of the system. So namely, the initial composition of the urns that you start with has a big impact on what happens in the limit. And if what happens way back in time has a big impact in the evolution of the system, then this suggests two things. First, estimating where the this network started from. So suppose someone didn't tell you who came, like the order of individuals, they just gave you the adjacency matrix of your graph, and they told you try to find where this network originated from. Then estimating where the network originated from, this sort of initial seed problem, should be doable. Whereas if there is an abrupt change at some point in the evolution of the system, there was a shock to the system, estimating when the shock happened might be hard. Okay, and sort of there should be long-range dependence in the system. So what I'm going to tell you is so continuing this sort of this change point detection, maybe some surprising math findings in this world. So change point detection is in the context of classical time series, is a very established, very important field. The basic setting is you have some sort of time series, and this time series maybe has at various times abrupt structural changes to how it's evolving. And you want to understand and find when these abrupt changes happen to the time series, and sort of distinguish this from inherent just stationary fluctuations of the time series. So for example, suppose you look at life expectancy. So I got this from the Associated Press early on at the beginning of the pandemic, sometime around 2021, I think. So if you look at life expectancy up to around 2021, so there are inherent fluctuations. There's a nice slowly increasing trend in the life expectancy, but there are abrupt changes. So for example, the 1918 pandemic, a major drop in the life expectancy in the US, again, World War II, major drop in the life expectancy, etc. So this is sort of one-dimensional or two-dimensional time series. But these same sorts of questions make sense in the context of networks. So we came to this actually from the world of neuroscience. So in the context of neuroscience, people were interested in, they were analyzing brains of patients experiencing epileptic seizures. And the hope was, if you can carefully monitor the signals across these brains, if you can quickly detect when there's an epileptic seizure about to happen, then maybe some sort of intervention would help these individuals. So what's the basic sort of methodological question? Suppose you have temporal network data. So in the context of network time series, they had time series observations at various locations in the brain. But another mechanism, this is what we'll be interested in, is suppose you have observations of the adjacency matrix at all or some subsamples of time points in the network. And suppose the network experiences a shock at some point. Okay, so context of social networks, say Twitter or X or whatever it's called at this point. Suppose Twitter is evolving in its whatever fashion, and then someone enters the system, a politician or someone, and suddenly changes the way that people behave on Twitter. So the network experiences a shock at some point. The question then is, can we detect this change point from observations? And to understand this, a natural question is, can we understand how structural properties in the system change? Because if we understand how structural properties in the system, like degree distribution, etc., change, these might give us ways to actually estimate when the change occurred. So now let's get back to sort of probabilistic questions. So the network model I'm going to think about is a much simpler version of the previous part of the talk. So fix an attachment function f. So this attachment function measures at any given time, if you have an individual of some degree, then f of that degree measures their popularity, and it tells us how popular the new individuals entering the system, how they measure the popularity of individuals. Okay, so at each stage, a new vertex enters the system, and again, I'm going to be thinking about trees. You can think about versions of this for non-trees as well. So at each stage, a new vertex comes into the system and connects to one pre-existing vertex. And the probability that it connects to a pre-existing vertex u in the system is proportional to its popularity, namely this function of the present degree of that vertex. Okay, and I'm going to call tau n. So we have a sequence of trees, and I'm going to call tau n the state of the network at time n. Okay, and so sort of this one of the more well-explored models is the so-called preferential attachment model, f of k, which is k plus alpha. Can't see over here, but I think so. An example of an exponentially growing time series is, for example, the number of citations to this paper, Emergence of Scaling in Random Networks. So I think a year ago, this had something like 40,000 citations. So this preferential attachment was brought to the like the network science community in this work of Barabasi and Albert, of course, known further ahead in the 1920s in the work of Ewell and Simon and so on. So this is one example. So here what we're saying is the popularity of individuals is proportional to their present degree plus some parameter alpha, like 2 or something. And the reason why Barabasi and Albert introduced this is they were searching for simple mechanistic rules to explain why many networks that they were observing at that time seem to have heavy-tailed degree distribution. And so if you look at the number of vertices of degree k, then what they verified numerically and then proved by Bolobach, Riordan, I think Spencer and Tusnadi is the proportion of vertices of the empirical degree distribution converges as the network becomes large, and the limit degree distribution has a heavy-tailed exponent of the form alpha plus 3. Okay, so where alpha is this parameter over here. So in particular, what one might think this alpha, it's just some constant. Why should it play a big role? We're basically saying degree, we're interested in measuring the popularity of individuals as basically their number of friends that they have. This parameter alpha does play a significant role in this system. So now let's think about a change point model in this framework. So the standard change point model is the following. So fix gamma in the interval 0 to 1. And now suppose our system is happily evolving up to time n gamma using this function, where I measure individuals by the number of friends that they presently have, plus this parameter alpha. But then something happens at time n gamma, so the network experiences a shock. And now after this time, the way that individuals' popularity is measured is their degree plus beta, a different parameter beta. So we have results about general FNG. This is just as an example. So remember, so this is, I'm going to rescale things. So gamma is this parameter between 0 to 1. So this is an audience question for people who have not jumped ahead to see the spoiler and or who have not looked at the papers and know of the results. But so I've sort of rescaled time between 0 to 1. So 0 actually corresponds to network size 1, gamma corresponds to n gamma, this corresponds to n, and this picture looks like, so what this is trying to convey is, suppose for a very small amount of time, let's say gamma equals 0.0001, I let the system evolve where individuals are measured, their popularity is measured according to their number of friends plus alpha. Now, if I ran this, if I didn't do any change point, if I just ran this forever, or not forever, until it became of size n, using this function f, I know that the degree exponent is alpha plus 3. Now, once again, suppose I didn't do any change point. I just use this function g, the entire stretch. So the entire stretch has this purple colored function. No change point, then the degree exponent is beta plus 3. So here, for a very small period of time, I use this I use this alpha plus 3 function, or degree plus 3, I'm sorry, degree plus alpha. And then after that, I use degree plus beta. So sort of let's assume that the degree distribution converges. Any guesses on what the degree exponent is? Sort of hard to do this over Zoom. Okay. So I will sort of tell you the answer over here. So the degree exponent is, in this setting, is always alpha plus 3. So this thing over here, I'm sorry, this thing over here, this beta in particular plays no role in sort of at least in the extremal behavior of the degree distribution. It will affect the degree distribution, which is what one needs to estimate the change point, but it plays no role in the actual degree exponent. Okay, so whether gamma is equal to 0.01 or gamma equals 0.0000, whatever, lots of zeros over here and then a 1, this initializer function, this function always wins. This function cannot change the extremal behavior of the degree distribution. So just to maybe slowly conclude, so one can think about general versions of this change point where you have some general function f measuring popularity of individuals that's used to measure popularity of individuals. When new vertices enter the system experiences a shock at time n gamma, and then after that, a different function g is used to measure popularity of individuals. So the picture looks like this. And once again, so what we were able to show with Sayan Banerjee and my student Ian Carmichael is one can look at the degree distribution of your sequence of networks, and you can show that these degree distributions, at least in sort of the fluid limit scaling, they converge to some smooth continuous functions. And these functions can then be used. So the first thing, structurally, what happens is, again, under technical conditions on F and G, irrespective of how small gamma is, this initializer function always wins. So the degree exponent of this graph without change point is, if you just run this with the function f, is some delta. Delta could be infinity, namely you have some sort of exponential degree distribution. Then the model with change point is also the same delta. So this function g cannot change the degree, at least the degree exponent of the corresponding graph sequence. But the degree distribution itself does change. And so what you can do is you can monitor changes in the degree distribution. And so you can look at the degree distribution when the network is of size something like n over log n or something. By that time, the degree distribution, you should have some sort of good idea about this if there is no change point. And become alarmed basically the first time this degree distribution starts to show some sort of fluctuations, starts to show big changes. And so this sort of like in words description gives an estimator, a suggested estimator for detecting when change point happens. And so then one can prove sort of these change point, this estimator is sort of consistent. More refined properties about all of this is completely open. Okay, so this is about it. Sorry, let me just skip over the last part of the talk and just jump to the end. So just to conclude, I've tried to give you an idea about two areas in dynamic network models, one about attributed network models, and the second about networks experiencing change point. I've tried to show you two, at least probabilistically, not super complicated models, but which still seem to show that one needs like non-trivial math to analyze what's happening. But generally this area is completely open. There are lots of interesting open questions. You know, these are just some of the very basic questions that we've been able to think about. Even things that we've thought about, you know, are far from optimal. So for example, at the end, I told you about some change point detection estimator, and I told you about these change point detection estimators being consistent. But if you actually see the performance of these estimators in simulations, even in ginormous network simulation sizes, like simulated these systems of size 200,000 or something, and the change point happens over here, sort of what the estimators do, they're slightly close to the actual change point, which is this red line over here. But you know, consistent means as n goes to infinity, even for large system sizes, sort of still things look far from stationarity. So there are tons of open questions in this area. Okay, so that's my basic conclusion over here. Okay, thanks.
Thank you very much for an extremely enjoyable talk. I have a quick question to get us started, which is something rather naive. Could you say something about where the minimization problem that Jonathan Jordan came up with, where does that come from?
Sure. Yeah, so that's a great question. Let's try to think, is it over here? So, what he was interested in was analyzing the degree distribution of the graph. So as a starting point, what he considered was, so suppose you look at, let me try to set up some notation. So suppose you analyze the following. So you look at all vertices of a specific type A, and you sum over their degrees. So let's call this YA n, when the network is of size n. And so suppose you look at this quantity, YAN, A belonging to your space of attributes. So this is, you know, before going to the degree distribution, this is a k-dimensional, I probably have to normalize this so that I think probably by 2n or something, so that it's a probability mass function. But this is maybe initially a macroscopic functional that might be easier to analyze. So what he showed is this macroscopic functional, sort of using stochastic approximations, this macroscopic functional sort of stabilizes to the unique minimizer. So it converges almost surely to the unique minimizer of this quantity. Mm-hmm. And starting from there that was a starting point of the degree distribution analysis.
I see. Great, thank you. Does anybody else have any questions? I can certainly ask another one. My other question is, so do you have any intuition for why the tail exponents for PageRank don't depend on the type? This seems kind of surprising to me.
Yeah, I mean, so that's a good question. Let's go back. So maybe I'll tell you one more surprising thing. Where is the PageRank? somewhere over here, maybe. Right. Okay. So the sort of, well, one reason is basically, at least for trees, the PageRank distribution, it is more global in the sense that it depends on vertices, of various types, not just your immediate neighbors, but neighbors beyond that. And because of this sort of weighted averaging, this is sort of the reason why the tail exponent doesn't depend on the attribute type. But what we don't know is the slightly so we have some math result, but what we don't know is the following. So I apologize. So let me just get here. So what these two computer scientists, Chebolu and Melstead, what they showed is this following amazing fact. So suppose you have a network which you don't really know, you're able to explore it using local moves. But now what you would like to do is you would like to sample a vertex with probability proportional to PageRank score. So vertices with higher PageRank scores have a higher probability of being sampled, as opposed to, you can think about other sampling schemes like picking a node at random. This is a more complicated sampling scheme. But it seems really strange because we're saying we don't really know what the network is, but we want to now sample the graph according to PageRank scores. So what they basically showed is for these directed trees, what you can do is you can sample vertices probably proportional to PageRank using the following local scheme. Pick a vertex at random in your graph, and then independently do simulate a geometric random variable with this parameter 1 minus c. And now what you do is, starting from this randomly selected vertex, you use the edges to traverse the graph, and you do this for g steps, these many number of steps. And wherever you end up at, you stop over there. The vertex that you stop at, that vertex, you have sampled, the probability of sampling that vertex is with probability proportional to PageRank. So okay, so I'm running out of time. So, okay, amazing. This is, I find, an amazing fact that they prove. Now, the reason why this is, for us, turned out to be very surprising is in settings where you're trying to sample individuals, like you have vertices of two types, minorities and majorities. Minorities have higher propensity of connecting to other minorities compared to majority vertices. Majority vertices have equal propensity of connecting whether to minorities or majorities. What we were, through sort of linear algebra, what we were able to show is if you sample vertices with probability proportional to PageRank, you're actually able to find minority vertices with reasonable chance, like with probability not going to zero, even as the proportion of minorities become rarer and rarer. And this is not the case with other sorts of sampling schemes. And so why this is true, we do not know. I apologize, long.
No, that's quite all right. Thank you. I think I'm going to stop there. Gesine had a question in the chat, but since she's had to leave, that's maybe there's maybe no point in asking it now. So what I'm going to do is I'm going to stop the recording, and then I'm going to propose that people unmute themselves and we give Shankar a big round of applause.